We're going to go ahead and start. I know it's close to the end of the semester. Everybody's focused on projects, and maybe there's lots of other people watching online. We'll see. But I actually spent a fair amount of time over the weekend reading your project proposals. So I think almost everybody should have feedback that came back through B courses. I think there were a couple of, there might be a couple of exceptions. But anyway, so there were a number of people that did talk about various aspects of needing load balancing in their projects. So it seemed like a good time to go ahead and talk about that here. So first we're going to do three little flashcards for speed up curves, so you can look at them and tell me what is the problem with this particular program. Okay, so here's a speed up curve. This one looks pretty good, right? Anybody see a problem? This is one of the 12 ways of fooling the masses kind of thing. So anyway, okay, look at the axes very carefully, right? Okay, so yeah, you got it. So the problem, of course, is that the y-axis is not labeled like the x-axis at all, and so in fact the speed up looks like this. All right, and it might have been easier. It would have been more obvious if I'd shown you the speed up at 1, which might have been a significant slowdown. So this happens because you've got a slow runtime system. Like your whole thing is slow. You may be speeding up very well. As you add more nodes, it gets faster and faster, but you start with a really slow program to begin with. And this whole speed up curve would look great if, by the way, I pick as my serial performance number this parallel code running on one node, right? So this is kind of picking a fair baseline, which gives you speed up that looks like this, where the performance you're using on T1, the running time on one processor is actually a really fast implementation. And so you just need to be a little bit careful. It takes a while to even cross over 1 here when you've got such a slow runtime system. And so the projects that I would say I worry about this kind of a speed up curve, which you won't even see probably because you won't use some other kind of implementation for t equals 1, is if you're using some runtime, let's say machine learning, there's probably 50% of you are working in some kind of machine learning algorithm, and you want to use TensorFlow or you want to use some other kind of a framework, and you have no idea what's going on underneath it. So anyway, just to be aware, one of the questions that some of you got back was, is there a way of getting some handle on some absolute performance? Like, is there some flop rate you can measure? Can you at least get some breakdown between communication and computation, things like that? Okay, speed up. Example number 2. So this is always a little bit worrisome. I used to try to publish papers that had things that looked kind of like this. So what's the problem with this speed up curve? So once again, black is the ideal line, blue is my measured speed up. Well, okay, so it's superlinear, which I have to tell you makes reviewers of papers extremely nervous when you show superlinear speedups. So what are some legitimate reasons why you could get a superlinear speedup? Have you seen them so far at all in any of your projects? Probably not. You're probably so you can get superlinear speedups because actually you have more cache, more fast memory cache in the aggregate system when you keep adding more processors. And so sometimes your problems that didn't fit in cache on one node, if you're doing strong scaling, they will fit in cache on a larger number of nodes, and so the whole thing will run faster. So you can see superlinear speedups. But if you're going to show something that has anything other than a little bit of measurement kind of perturbation in there, you should definitely try to explain why you think you're getting a superlinear speed up. Okay, this is the more common speed up curve. This is what we typically see. And the problem with a speed up curve like this is you really don't know what's going on, right? So what could be happening is you could have synchronization overhead, you could have load imbalance, which is the main topic of this lecture. You could have lack of parallelism, which is going to look like load imbalance. So I'll say a little bit more about that. But this is very typical. This is a strong scaling curve. Almost any strong scaling curve, I would say probably really any strong scaling curve, will eventually look like this, because a problem that is large enough to effectively use a huge number of processors, like if this went out to 10,000 cores or something like that, is probably not going to fit on a single core, or at least a single node. And so so when you try to have a single problem size that has a speed up curve like this, you'll see something that looks like that. Okay, so what are the causes of poor scaling, as in the previous slide? Well, you can have high synchronization overhead. You can have processors that are spending a lot of time sitting in barriers, or processors waiting on locks. It's going to be a little bit harder to debug, to find the performance bugs if you have locks that are not all together. It's pretty easy if you're using a bulk synchronous program that has barriers, and that should be true, I believe. If you're using some kind of a MapReduce type framework, you ought to be able to hopefully measure the things. I don't know what the guts of those look like and what they expose to you in terms of running time, but hopefully you can measure something that looks like that. So here's a problem with what I'm showing here is a very wide barrier. Okay, so what this is a bad barrier implementation, and that can also come up either because the person implementing, well, basically because the person implementing the programming model that you're using or the hardware itself is just really slow at communication. So if you're going to run an application on a Ethernet network, it can have terrific load balance. Everything is doing exactly the same amount of work on every processor. You're going to have poor scalability because you spend a lot of time sitting in barriers, even if you have no communication, right, other than maybe some initial work distribution. So that's a perfectly well load balanced program, but a slow barrier. More commonly, or at least more, what we're going to talk about more here is that when you have load imbalance. So here it could actually be a fundamental load imbalance problem, such as lack of parallelism, where you can't, no amount of load balancing will help. And this is, by the way, a common thing that I hear people trying to do is they say, oh, my program isn't load balanced, I will implement a better load balancer, and that will fix my problem. Well, you better make sure that you actually have enough work to evenly balance, and that you don't, for example, have one chunk of work that is equal to 10% of the running time of the total amount of work that you need to perform, because then your speed up is going to be limited to 10x no matter what you do in terms of load balancing. You can also have serial bottlenecks, some kind of an Amdahl's law problem. So here's, just in our cartoon, we have a faster barrier here. The blue part is now thinner in terms of the running time. We have load imbalance in this one, and we have a serial bottleneck in this particular scenario, which looks like one of the threads is taking a much longer amount of time. And so how are we going to go about measuring this? Well, it's pretty easy, but you need to be a little bit careful about how you go and think about the running time. So we, in particular, let's talk about measuring load imbalance. So sometimes it can be hard to separate load imbalance from high synchronization overhead. Basically, the left-hand picture where you're spending a lot of time calling synchronization routines because they are themselves very slow, whether it's locks or barriers, versus load imbalance where some of the processors are just sitting there idle waiting for the other processors to compute. So how do you distinguish those two? Well, you can put timers around your barriers, the age-old, printf, so start clock, stop clock, and printf, probably if you're running on distributed memory, the amount of time it takes for the barrier is long enough that you should be able to measure it without any problems. If you're inside of a shared memory node, you may have a little bit more trouble with the timing granularity, but I think the barriers are still going to be slow enough you can measure them. But a very common problem is that people measure all of these across your processors, and you may have a very large number of processors, right? You're running 100 or 1,000 processors or 1,000 cores, and you say, well, I don't want to look at every one of those numbers, I'll just average them. Well, so what's the problem? Now you have no idea whether you're in the left-hand scenario on the previous slide, which is just a slow barrier, or you're in the right-hand scenario or something in between, which is just one serial bottleneck. So you do need to actually keep all of the times that you spend and either look at all the values or histogram them or something so you can say, oh, 95% of them were all said that the barrier time was, I don't know, a second, and this one guy, or well, what did I say, 5% of them said that it was only a tenth of a second. Well, that means that those 5% of them are this serial bottleneck guy, and they only spent, a tenth of a second sitting at in this barrier, because by the time they got there, everybody else was there. And so you need to separate those two out. It's pretty obvious when you think about it, but I can tell you that oftentimes people just sort of average them, and then they have a hard time sort of separating what the performance data actually means. You may have already seen this in your homework assignments as well. So spin locks. Spin locks can be, so this is where you write a piece of code yourself that says something like test to see if the lock is available, and if not, just sit there in some kind of a loop, or maybe even go off and do a little bit of other stuff if you've got something else that you can do. That can make it really hard to tell whether you're doing useful work or you're not, so you need to be careful about that in measuring measuring these kinds of things. And by the way, a load imbalance can be caused, well, it can be caused, as I said, because you just don't have enough parallelism. If you don't have a parallelism, there's no way you can balance the load. But it can also be caused by hardware problems. It can, and this is where you will see sometimes little bits of superlinear speed up because of things like cache behaviors, dynamic clocks, or things like that. And so that's something else to look at. Now, you know, besides just putting timers and printfs in, there are performance tools, at least at NERSC. I don't know what the performance tools support. And does anybody here know what it's like for any of these machine learning frameworks? So, do you get any kind of good performance information out of TensorFlow or any of those other things? Okay, Spark or Ray, we built it here. So hopefully you're putting those performance tools in there. But here's a nice graphical user output from CrayPat, which is the Cray Performance Toolkit. And here's a link to some of the things that are on the NERSC website if you want to look at other performance tools that are out there, like HPC Toolkit, which I think doesn't have a space in it, but anyway. Okay. So, you know, so we kind of, so load imbalance is only one of the problems that can come up. Let me not spend more time on this because I think you've seen all of these different things, but you know, how do you recognize something that's load imbalance versus other kinds of problems that we saw in those little speed up cartoons? It is time spent on the synchronization that's high, but it's uneven across the processors. Okay, so what are we going to do? We'll do a little bit of, I guess, motivation of load balancing. We've talked a little bit about what the problems are. I'm going to try to break it down into 3 different categories of load balancing algorithms. There are thousands of papers out there in the literature on load balancing, and I would say this is one of the worst examples of computer scientists not citing the prior work or even being familiar with the work. A lot of these algorithms or heuristics and things like that get invented over and over again because it can be hard to figure out when somebody else is solving the same problem. Well, that's a generous way of looking at it. But anyway, so we're going to talk about, we've got a set of tasks like this, and they can be organized in various ways, and they may be communicating. Those are the little blue lines. They may only get created based on dependencies. So those are the little black arrows in between them. And so some of these, there's different factors that affect what kind of a load balancing algorithm you want to use. These include things like the cost of each task, the number of tasks, the variability in the cost of the number of tasks, the dependencies between them, the black arrows, the communication between them, the blue arrows, and at what point do you know information about any of these things? At what point do you know the cost, the number of tasks, the dependencies between them, and so on? And so load balancing is really about where to execute each processor and which processor to execute on. There's a separate kind of a scheduling question, which is when do you execute it, and these often get mixed up, and we will in some cases talk about scheduling as well as load balancing today, but there really are two not completely independent pieces. Obviously, when you are scheduling something, you can only schedule the things that have been assigned to that processor for a given processor, but they are somewhat separate parts of the problem. Okay, so the first thing we're going to look at is we're going to look at the question of what happens when you have tasks that are variable, and they're just shown here by the area of the circles. So, for example, the easiest case is where we've got a whole bunch of tasks to run, but they're all exactly the same size. Okay, so this would come up in matrix multiply. We're doing dense matrix multiply. We have a whole bunch of tasks in the matrix, and each one of them is going to be a block, a matrix multiply of size B by B, and so each one of those should have equal cost, okay? Direct n-body methods, I think Jim talked about n-body last week, and so the simplest case where you're just looking at all pairs of particles, not when you have some kind of a tree, that would have fixed size tasks. So every chunk of particles and particle interactions would be a fixed size task. So it's a little bit harder if you have variable size tasks, but you actually, but you have the estimate of how many, what their cost is, and probably some estimate also, or the number of tasks that you're going to have. So this can also come up a lot in, and I would call these, we'll talk about these as semi-static sort of load balancing approaches, where, for example, you have a sparse matrix algorithm, but in the middle of the execution, before you start, say, factoring your matrix or whatever you're going to do with it, you can, or even if you're going to just multiply that sparse matrix times something, you can do some analysis to figure out how big each chunk is. And you can use that to, first of all, to partition the work into tasks that have equal size. So that's where you would use something like graph partitioning, or you can also use it to, if you know in advance that you've got some very expensive tasks and some very cheap tasks, you can use that to come up with a better load balancing approach. So if you know the cost of each task. The hardest case in some sense is where you don't know anything in advance. And so as you're trying to execute your actual algorithm, not just in the middle of the computation, not in the middle of the application, but in the middle of, say, factoring a matrix or whatever, and this will come up in sparse matrices, you don't know how many non-zeros are going to get filled into the matrix, so you don't know what the cost of one of those tasks is going to be until you get there. Although in that case, they often run algorithms, like symbolic algorithms, to estimate those kinds of costs. Okay. All right, so even if you have, by the way, perfectly balanced computational costs at the application level, you can still have load imbalance. And these are a couple of the more well-known examples of where this came up. So one was in a supercomputing 2003 paper by a group, I believe, at Los Alamos, which was called The Case of the Missing Supercomputing Performance. So they had a problem that was completely evenly partitioned, equal amounts of work on every processor, and they saw performance numbers. So this is number of nodes here, right? And this is the slowdown of percentage that they were getting across them. So you can just look at this as the relative running time of each one of the processors. So if everyone is doing the same amount of work, why do they have a profile that looks like that? I'm not quite sure what was going on in here, but what some of these other things are is they're operating system daemons that are waking up on one core of one node of your supercomputer, or actually one node in a set of nodes, and says this node is going to be responsible for doing a certain amount of work, or there's something else going on, that's some extra, say, operating system overhead that's being run on a set of nodes over there. So unbeknownst to you, kind of as the user, and this was, what you can see here is what they're measuring the running time of this application. And if all they do, and by the way, that was a comment generally on the proposals, if many of them were very good in terms of saying how you're going to break down the performance numbers, but if all you're going to do is measure wall clock time, what you're going to see out of this is, here's my wall clock time. And you can still do speed up curves that say, here's my wall clock time over here, and here it is when I do more processors or something like that. Obviously the curves would change there, but you're going to be measuring the top of those peaks, right? Because you're going to be measuring the speed of the slowest processor, and you may or may not see speed up. Who knows what you'll see? Maybe it'll run faster when you get more nodes, but it'll be sort of completely arbitrary because it's based on these, say, operating system effects, which are causing these peaks, as opposed to measuring something that's actually useful. I mean, it is the wall clock time of the application, but there's a problem to be fixed, which is how do you get rid of those peaks? And they found that they could adjust the operating system in order to make these problems go away. This other one, which was done by Brian von Strahlen and others, who was at Lawrence Berkeley Lab, actually also a grad student here on campus, is more of a, it's even more kind of, was harder to find. So this is looking at two different applications running on different numbers, or sorry, it's one application running on different numbers of processors. So there's the red run and the blue run, but they're both running on the Cray XT4, and so what was happening? Well, this kind of variability you see in here would be sort of normal expected performance variability from things like caching. But what causes these big spikes? And it turns out that what happened once and this took a long time to figure out, was they talked to the facility that was running it. They went and did some more tests on it. What they found was the DRAMs in these processors were actually about to fail. So they hadn't yet failed. So in the hardware, some of you know, there's errors that happen, and then there's error correction that happens in hardware. So there's some extra bits that are kept around, and there's a little algorithm that says, oh, if these bits don't match what's expected, I'll go and try to correct the error. And so these error correcting codes, ECC, on the memory, were actually just running frequently to correct the errors. And that error correction, even though it's running in hardware and is itself a very fast algorithm, is enough to slow down the performance in a way that looks like that. So you've got to be very careful, because load balancing can kind of sneak into your application, even if you as an application programmer are absolutely sure you've divided up the work evenly. Okay, so static scheduling is very common in scientific computing. So some of you are planning to work on scientific simulation proposals. A number of you very reasonably have said, I'm going to solve, say, a fluid dynamics problem. I want to do it on a three-dimensional cube. So that's going to be a problem that should be very easy to load balance, and you can load balance it statically. So you're going to have just equal-sized tasks. There's going to be these cubes. Maybe you'll have a little bit of funny business because things don't quite divide into p. You know, are you going to use a cube root of p, or what are you going to do? But basically, you'll have a really easy problem in terms of load balancing, to the point that you really won't think about load balancing other than making sure you don't have some peculiarity leaking into your execution. So we've got n tasks that we want to schedule on p processors. We'll just give each of them n over p tasks, so completely obvious. And you did this in the homework 2. So if n is known in advance, and by the way, compilers, there's a bunch of the literature I'll talk about here, which is compilers trying to figure out how to automatically schedule and load balance loops. A compiler that, if it knew the value n as a constant, then it can actually divide, at compile time, can divide things up. But normally, it will have to generate some code that will figure that out at runtime. And but still, a pretty trivial amount of work that has to be done at runtime, divide n over p. And so this is, of course, something a compiler can do if it doesn't have any dependencies. That's kind of an orthogonal issue, but if all those iterations can be run in parallel. And it's called self-scheduling typically in the compiler literature, but it's still basically this load balancing problem. Now, a harder case is where we have different size tasks, and we're trying to do what's called a classical problem in, I guess, scheduling and in computer science called bin packing. So we're just trying to take these different tasks, which I'm now showing as rectangles, and putting them into these p bins. So we've got n tasks into p bins, but they may have different weights, and so you really, figuring out what's the optimal way to pack them in order to minimize the total execution time is considered a classically hard problem. It's an NP hard problem. Almost every problem, other than the one I just talked to you about, which was the very simple static number of tasks that are all equal in size, we're going to run into NP hard problems all over in scheduling. So most problems that aren't completely trivial are going to end up being NP hard. So in principle, we can calculate the best possible load balance for this by looking at the best way of packing these tasks into bins, but in practice, it may not be something we can afford to do at runtime. We don't know those tasks until runtime, for example. And even if it's a very large problem, even doing it offline can be prohibitively expensive. So now that's not hard enough. So now we'll look at an even harder problem, which will in some sense turn into an easier solution, which is if we really don't know anything about the cost of the task, the size of each one of the tasks, until you're in the middle of executing the task, you can't even use a bin packing approach because there's no things to pack in the bin. You don't have fixed size things. So then you tend to use something called self-scheduling or work stealing, and I'll talk quite a bit more about that, and I'll talk a little bit more about when we have tasks, because a lot of times these will come up as a set of tasks that have dependencies between them. So what are we going to do, though? We're going to build some kind of a shared task queue, and we have a bunch of workers, and then we have a coordinator, supervisor, whatever you want to call it, that holds a queue of all of the tasks, and just grab tasks from it. So lots of papers just on this particular problem. These are some of the older ones. I think there's probably even more recent work. As I said, a lot of this gets done over again in different contexts. So people in the cloud community, these are old HPC results, mostly shared memory, maybe with the exception of the tapering thing. They did do some distributed memory work. But most of these I think these are all working on shared memory machines. So self-scheduling, the original one that I talked about, you're just scheduling individual tasks. Okay, so what's the problem with that? Typically, the problem is you're accessing a shared queue. You need something like a lock on that queue. If you've got little tiny tasks, so one iteration of a loop, all the processors are just going to spend all the time banging on the queue. Okay, so the most obvious thing to do is to say, oh, instead of doing that, we will give you a chunk of work, and you can just have a kind of an engineering solution that says I will have a chunk chunk of size k so that I don't have to access the queue so frequently. I will lose a little bit of load balance when I do that, right? Because at the very end I'll have chunks of size k as they kind of finish things out. So it might not end quite as evenly as if I had a chunk of size 1, but it's a perfectly reasonable way to get good load balance in here. But now the question of how you pick the size k is a trade-off between how well you want it to load balance. If you make k too large, you'll end up with these big chunks of work at the end that only a few processors will be working on, and a bunch of them will be idle, versus making it too small and then all the processors spend too much time accessing the queue. There is a paper by Cook and Polychronopoulos that says, well, we should pick the chunk size k sub I at the ith iteration, or the ith access to the task pool, given by this formula, what's R over P, where R is the total number of tasks that are remaining in the pool and P is the number of processors. So what that says is that at the beginning, I have, let's say that I start out and I have 1 million tasks, and so I divide them up into 1 million over P pieces, and I take one of those chunks of work. But as you get closer to the end of the execution, you always look at how many tasks you have remaining and divide those up evenly, rather than just every processor always taking 1 million chunks of work. And so that tends to work well, because even if the tasks are being created dynamically, then eventually you'll get to the point where you have an even load balance at the end. This paper, I believe, was actually not doing it for the case where tasks are being created on the fly. It was saying we've got all the tasks up front, but we don't know exactly what their weights are, so we'll divide them up into roughly equal sized chunks, but every time you access the queue, you get a smaller and smaller chunk. So at the very end, there will be a little bit of there will be some time to sort of smooth out the end. Tapering was said that it was a result by a student here at the time, Steve Luco. It says that you change the chunk size based on the cost variance, which you estimate from the history. So you're basically watching the costs of each task as it executes. You record that, and if it has a very high variance, then you will use a smaller chunk size than if you have a very low variance. Because if you've got a low variance, then you can really estimate pretty well, and you can grab a big chunk of tasks and use that to predict, to make sure that the load gets balanced evenly. And there's another algorithm called weighted factoring, which was getting at the issue that you may have heterogeneous processors in there, so you may want to weight the chunks of work by the processor speed. I think that one was actually more of a theory paper on that algorithm, and proved some results about it. Okay, so now, but those, we're all talking about shared memory, and so you've got this shared queue, and it's got a lock, and so there's a little bit of a bottleneck that you need to worry about, so you're trying to avoid that. But now what if we've got distributed memory? Well, we can use a distributed task queue, or what I'll call a bag, for a reason I'll say in a minute, where you've got one of these queues on each one of the processors, and every processor can pull work from one of the processors that has work in its queue, or a busy processor can push work. So you have both a pull and a push strategy. So when are these going to be a good idea? Well, first of all, if you've got a distributed memory multiprocessor, you really do not want to have a shared queue sitting on one processor, because it's just all the processors will spend way too much time communicating. So you need to go to this kind of a distributed approach. Even on shared memory machines, it's often the case that what you want to do to avoid lock contention overhead for accessing that queue, especially if your tasks are a little bit too small, or if you make them big enough, then you have load imbalance problems, is you make a separate queue on every processor, so most of the accesses will be to a local queue. Even though you have to use a lock, it will, because other processors may be trying to steal from your queue, you will almost always succeed in accessing your own, the queue that's local to you. When you're doing this kind of load balancing this way, you're pretty much ignoring locality. So you're mostly allowing tasks to just sort of roam around the system, especially if you're going to push tasks out, because every time you make up a task, you push it out to another processor. If there's locality between tasks, they're using common data structures or whatever, then you will not be optimizing for that at all. And if you knew what the costs of the task were in advance and the number, you would probably use a static approach or a semi-static approach, where if you get to the middle of, and this is very typical in computational, in simulations, in scientific simulations, where you may not know, before you start running the program, how large the tasks are going to be, but at a given point, now I'm going to have 1,500 tasks or whatever, and so you can sort of take some time, figure out the right load balance, and execute after that. So that's a pretty common strategy. So just for those of you not computer scientists, so I've been talking about a queue. That's really a first in, first out data structure, right? So just like going to the bakery or whatever, that's the canonical example. You get first in line is the first person to get served. Whereas a stack, which we'll also use in here, would be a last in, first out data structure, where you always take the most recent arrival and execute that task first. And then a bag, which is what I referred to up here, sometimes called a set or multi-set, but it's really doesn't even necessarily have any nice mathematical properties, but it's just an unordered set of things is what I'm using there. So once we go to these distributed queues, we've lost any, or at least we've lost a lot of the ordering guarantees that we would have had in a shared queue, where you're sure that the first task that was executed, or the one that's at the top of the queue, is the oldest thing in the queue, whereas whatever happens to be in your local queue may not be anywhere close to the oldest. Okay, so there's a lot of different ways of finding a donor process, or if you're using task pulling, which is the more common, or task stealing, the more common technique. Whereas if you're using task pushing, we'd call it an acceptor of somebody that's accepting the task. But let's just kind of worry about the stealing, and we'll talk about the pushing down at the bottom. So the first thing that we can do is just have every processor use a round-robin approach. So every processor looks at, keeps track of the last place it looked for a task, whether it got one or it didn't, and moves it along, adds one to it, and then just wraps around looking for more work. Okay, so that's an easy thing to do. You want to make sure, and this is a common bug that people put into programs, so just be aware of it, is you don't want to all start up thread 0 and all look for work on thread 0's queue. That's obviously a very bad idea, because it creates a bottleneck at thread 0. So, but every processor can just keep track of its own counter and kind of look around independently. And the other thing you could do, which might be better, is to say, well, better in the sense of giving you better load imbalances, to have a global counter that keeps track of where the round robin is at, because now every processor, when it comes to look for work, is going to look at the last place, or the last place plus one, that another processor just looked. So you're much more likely in the global case to find work than you are the local one, because the local one, you could have two processors that just sort of run behind each other, and the second one can't find any work because the other one has already picked it up. Although presumably that first one goes off and is busy doing work, and so eventually the second one will pass it. But that's sort of another strategy. This has the disadvantage that you've got this shared state, this global counter that you have to keep updated. And on a distributed memory system, that can be quite expensive, as you know. We can do randomized stealing. So whenever a processor needs work, it computes a random number between 1 and p, and it just goes and steals from that processor. Actually, yeah, and it can also, or you can do randomized pushing, is whenever a processor creates work, it computes a random number and sends that task to a remote processor. In all of these schemes, by the way, I guess in all of these schemes, the question of termination detection is not trivial to implement. And this is one reason, by the way, where if you can find a good implementation of a load balancing distributed work queue or stealing queue or something, that you don't want to necessarily rewrite it yourself, is because the question of figuring out whether all of the work in the system is completed is hard, because you've all got, as soon as you've got multiple copies of the queue, you don't know when the queues are empty. I mean, even in the case where you have a centralized queue, you have to worry about the fact that some processors may be busy operating and are about to enqueue something in the queue. Okay, so, and there are papers on, you're basically trying to compute a snapshot of the system state to say, does everybody agree that they're all out of work right now? And so there's ways of doing that, both more scalable ways and less scalable ways of doing it. Okay, so just to summarize, we had kind of a static approach where we can just kind of put all of the tasks into the bins, whether they're equal size or variable size, but if we know them all in advance, if they're static, then we can, and we're willing to spend the time, we can actually compute an optimal load balance, although it is NP hard if the tasks are uneven. If we've got in the case which I think is most common in scientific simulations, where you know something about the tasks and the count in advance, in the middle of the execution, before you're going to go off and do some large computation, so you can do something to try to predict what the best load balance is here, and oftentimes that's what people do, is they run some algorithms such as a graph partitioner tries to divide things into equal parts, or even if they have some other fixed set of tasks, they'll look at them all and try to figure out what's the right way to schedule them. Dynamic is where in the middle of actually executing the algorithm, you're say stealing work from other processors. And this dynamic approach, which sounds most appealing, it's kind of the simplest to implement in terms of, other than maybe the termination detection problem, and as soon as you have some kind of uneven load, that's a non-trivial problem here, so why not just use a dynamic approach? Well, the problem is you really have, if you've got very large tasks that carry with them a lot of data, and you have to ship that data, you need to be very careful when you're doing dynamic load balancing that the cost of load balancing doesn't exceed the cost of the load imbalance that you were trying to fix, right? That the cost of moving things has got to be less than the cost of executing it remotely. Otherwise, there's no way you can win by doing dynamic load balancing. Okay, questions? Okay. All right, so problem set number 2. Now we're going to have dependencies between tasks, and we'll actually look at some theorems that are even related for the first case. But now I've got some tasks that can't all execute at once. So actually the easiest case is they can't all execute at once. So that's kind of the whole previous part of the lecture so far. And these would be things like where you've domain decomposed your problem, and you've got these equal pieces of work, and they're all going to execute together, at least in a given phase. And there may be a separate phase after a barrier where you have another set of things that are all independent tasks that can be run. They can be run at any time. They may or may not have some data that has to be communicated between them. So the second hardest is where there's some dependencies between the tasks, but you may know in advance what the structure of the task graph looks like. So for example, you could have chains. This would be commonly, if you've got a simulation where you run a bunch of independent things, I could write this as I put a barrier here, I run a bunch of independent things, I put a barrier here. But you could also just have a chain of things where you know that that's what the tasks are going to look like. Trees are very common, and we'll talk mostly about trees in this particular part of the lecture. General DAGs are going to be harder because now you've got some tasks that are waiting not just for its parent to say spawn that task, but for two parents to say we're both ready for you to execute that task. And this will come up most commonly in linear algebra, but in linear algebra algorithms where you're doing direct solvers, so things like LU or Cholesky factorization, where you're not an iterative solver. So in an iterative solver where you're just going to take a matrix and multiply by it, you will be in something much closer to, say, a chain approach, because you've got that multiply operation is a bunch of independent work that can be done in any order. You just have to make sure it all gets done before you move on to the next step. And the hardest case is where we don't know anything about the structure until runtime. Okay, so let's talk about task trees and task tree search, because it is an important class of problems that come up. Search problems can be, they can come up in things like games. We have a couple people, I think, that were working on games for their final project. So something like chess or Go. N-queens, I will just comment that N-queens is my most despised example to use in a computer science paper on parallel computing, because it's sort of completely uninteresting from every aspect of parallelism, but is a great way to test out your dynamic load balancing approach. So anyway, you just put n queens on a big chessboard of size n by n and try to figure out what's the, run that forward as a game. So let's see, optimal layout of VLSI chips, robot motion planning. I know we've got a couple people, I think, looking at robot motion planning. Some symbolic problems, such as sort of what's like a symbolic factorization algorithm, Grosvenor basis, or these are a couple of things that I've worked on in the past, or my students have, looking at phylogeny trees, computing those from a set of genes. So these tend to have a sort of a tree search kind of structure to them at some level. Some of these are very computationally expensive, and the parallelization looks quite different than it does in most physical simulations, where the name of the game is usually divide up the domain into pieces and run each one of those pieces on a given processor, or at least on a given node. And these are going to require some kind of dynamic load balancing to make any reasonable progress. So just to kind of make this obvious, here's a tree search problem. These are tasks we're trying to, let's say, nodes of our Go game, I guess, we're trying to play. We're making various moves here and trying to figure out what's going to happen, or some other kind of a search problem. And so what would happen, so what do we have? We can talk about the terminal node of the, which is one we don't want to get to. So these would be like losing boards, for example, and a terminal node that's a goal, which would be a winning board. And so we're trying to search through the tree looking for the blue nodes, but we may, if we go down this tree in depth first order, we're going to go find 3 red nodes before we find the first winning blue node. And that's just doing it serially. And so this is a particular kind of task graph that comes up quite a bit because it's a graph structured as a tree. It's a special case. Okay, so in this particular case, I'm assuming there's no common subproblems. That's why it looks like a tree. So I think Aiden talked about depth first and breadth first search, right, in the search and lecture, so I won't really talk about this other than to say, when I talked about stacks and queues before, a depth first search is using a stack, doesn't have much parallelism in it. Breadth first search has lots of parallelism in it, but you could be looking through a lot of things where you're wasting your time. You typically put things in a queue, but oftentimes the stack just doesn't have, it takes a long time to get enough stuff into the stack to make it actually get a lot of parallelism. So let me just talk about parallel search. Okay, so in parallel search, let's say we're doing some kind of backtracking search, and we're going to try to do this with static load balancing, just to make it completely clear why this is a bad idea. And there again, okay, so let's say that we just have 2 processors. So the problem is, at the top you've got a fork, and so one processor goes off and does the purple things, and the other processor does all of the cyan things, and obviously not very well load balanced. Here's what that same tree would look like on 4 processors. The first kind of 3 pieces of work are, or 2 pieces of work are the yellow and the green, and then the next one is the cyan continuing, and the last one is the purple. So obviously these are bad. It's a bad idea to try to do any kind of static load balancing when you have an unstructured tree search, unless you have unless you know something about the tree structure that is going to be very balanced. Okay, so oops, I think I did this in the wrong order. Okay, so let me talk about a kind of classical theory example that's going to help us out here, which is these problems are all hard, they're NP hard, but we can make some progress if we are just looking at things that work probabilistically, so results that we can prove with high probability. And I'm not going to try to do any of the probability analysis here, but what we're going to do is use randomized load balancing. And I talked before about randomized stealing and randomized pushing. Both of those will come up here, although in this context, these papers were talking about it in the context of, say, a search tree, a task tree. So I wanted to give it to you in that setting. But you can also apply these to just a bag of tasks that don't have any dependencies between them. So in this case, there's the kind of classical analysis is called balls and bins. We've got a bunch of balls. We're throwing them into bins, and we're trying to figure out how evenly they land in the bins. What's the load, if you will, of each bin in terms of the number of balls in that bin. So the tasks are the balls, and the processors are the bins. And here's the basic result that we're going to rely on, which is that given n balls that are thrown randomly into p bins, with high probability the maximum load in any bin looks like this. So this will be the worst case running time, which would be if n is equal to p, and this is what you'll often see is people talk about log n over log n. This factor, for those of you who are not computer science theory, you can sort of just assume, you can just make this, kind of ignore this for now. This says that for very large numbers, this is going to look like, this whole thing is going to look like 1. So it's going to be log n over log n. Now that's if n is equal to p. I would never write a dynamic load balancer probably for a problem in which you've got n tasks to schedule on p processors if n is equal to p. Hopefully you've got some other information you could use to just assign each one to a given processor. So a more kind of common case, which I've written over here, is if n is greater than p log p. And so, and then what you get is something that looks like, well, n over p, so that's the best you can do, right, is going to be expected running time, plus this theta factor, which is also got an n over p. It's a square root in here, but there's an n over p inside of it, so that's also good. That says it's a load balance. And then the load balancing factor in the top, which is log p. So that's a pretty good, it gives you still a pretty good bound, and this is the expected running time now. And by the way, we're not talking here about tasks of different weights. We're just talking about equal size balls being thrown into bins, although this kind of strategy will be used even if they think the balls are not of equal size. And so what is this? I mean, there again, this just says that we can, I mean, roughly speaking, we're going to have something that looks like very good load balance n over p, which is the best you can do. But perhaps the most important thing about this theory result is you want enough work to do that randomization is actually going to work well. So you probably want on the order of p log p pieces of work. Otherwise, you probably are going to end up in a less load balance sort of situation. So it's just kind of, you know, it doesn't say you can only use dynamic load balancing when that's the case, but if you don't have kind of p log p pieces of work that you're trying to randomly steal and randomly throw around the system, I would say you're more likely to, even in practice, you're more likely to end up and so that's the theory result that gives some backing behind the intuition, which is you need enough work to randomly load balance. Okay, so let me go backwards. So here's how it gets used in let's see. So there's a paper by Karp and Zhang, which was kind of the original one that says for a unit cost tree, that is tasks of equal size, where the parents have to be done before the children, and the tree unfolds at runtime, so we don't know the structure of the tree in advance. I mean, it could be arbitrarily kind of unbalanced or whatever. Then this is this result, which is that simple randomized load balancing is optimal with high probability. So ignoring all the details of the formulas and stuff, that's the main result. That with high probability, if you randomly assign these tasks to processors, you're going to get equal amounts of, you're going to get something that's pretty close to optimal load balance. And then the second result, or how it gets generalized, was done by simultaneously by Charles Leiserson and his student at the time, Bobby Blumoff, and Shoman Chakrabarty, who was one of my students working with Abram Ranade and myself, and we were looking at two different scenarios simultaneously. So they were looking at probably the more common scenario, which is work stealing, and we were looking at the case of work pushing. So what they say is that simple randomized load balancing are also optimal in the case where let's see. Where in both of these we're looking at the case where the task costs have variable size, or where they're variable costs. So now we don't have a tree with equal size balls, we have these bins with variable size balls in it. And in this case, I guess we're still relying on that basic theory result, but and so as I said, they're doing task pulling, and they're using, and this was what they ended up implementing in a system called Silk, Charles and some other students of his, and they say it's better to give than to it's better to receive than to give, right? So whereas we were looking at the case where you're pushing the tasks out. let's see, I don't remember if I have this on another slide, but one of the things that, just to look at it as we've got these two on the same slide right here, is there is a trade-off between these two in terms of locality versus load balance. So in this case where you're only stealing work from other processors when you have nothing left to do. And so most of your work is going to run locally unless somebody comes and steals it. And so if you've got some locality between the different tasks in the tree, you know, all the yellow tasks along a common chain, for example, needs some common data structure, such as a submatrix, then stealing is going to be better than pushing, right? Because you're going to be more likely to run a task that run a task on the same processor as its parent. On the other hand, it can take a lot longer to load balance things. So this will more aggressively load balance the work, because as the work is being made up, you're immediately pushing it out to other processors, so the load balance happens faster. So if you don't care about locality so much, this can actually be better. If you do care about locality, typically the work stealing is better than work pushing. Okay, so a little pragmatics, because a lot of people decide they might as well just go implement these things themselves. It's not that hard to implement some kind of a work queue, either in distributed memory or in shared memory. And by the way, one of the things you typically want to do is to grab a chunk, not just grab the minimum size work. So you have to figure out whether that's something that's built into the queue, or whether you're just going to put pieces of tasks of work that are already pretty big into the queue, or if you put smaller things into the queue, you can use these kinds of techniques I talked about earlier, where you start by taking a larger number of tasks when you're stealing, and then later on in the execution you may take a smaller number of tasks to give you better load balance. But you do need to worry about the granularity of those tasks in general, and the granularity of stealing. If the, let's see, if we've got our stack, and in Berkeley we make our stacks grow down like this, and so we've got the things that are coming into the stack and are being pushed onto the stack at the bottom and being pulled off here. So this is where we take things off of the queue, and this is where we take them off the stack, and they're all going into they're being fed into the bottom like that. So the least recently inserted thing, LIFO, would be coming off of the top. So so we're pushing these tasks onto the bottom of this queue, and we execute either from the bottom, that is which will be the most recent task, and then we send things from the top. So the point is that whether you're executing a task locally, or you're sharing, or you're stealing one for a remote processor, or even sending it to a remote processor, you have a different choice of which is the best task. So you typically want to always execute the most recent one, because if there is any locality between what you're doing in between your tasks, you want the locality that comes from the parent task to the child task, or even from a sibling task, that would be sitting at the top of the stack right here. On the other hand, if you're stealing, you want to steal something from somewhere pretty high in the tree if you can, because although you don't know what the structure of the tree looks like, and it could be that there's some really long spindly thing over here, and there's a bunch of really short stuff over here, most likely things that are close to the top of the tree are going to give you a larger chunk of work, and therefore amortize the cost of moving that work to another processor. So you typically steal from the top and execute from the bottom. Okay. Questions? Okay, and that idea is implemented in a number of different libraries, for example. We can use the randomization ideas that I talked about, and the techniques that I talked about before for randomized pushing and randomized pulling as well. So I think this is somewhat redundant with the other slide. Okay, so randomized work pushing, here's some speed up numbers that were done by Showman Chakrabarty. He was running on a distributed memory machine, a really old one, but really new at the time, which was a connection machine, a CM5, which was built by Connection Machines. It's a very faint line you can see here, which is the linear speed up number. I couldn't get the actual raw data anymore from something that was published in 1994, but you can see the actual running time that you're getting there. What he also did was, and this was because of the problem of superlinear speedup in some of these kinds of tree search algorithms, where you can just get really lucky in a parallel tree search and find your goal, for example, in a time that is much less than the total amount of work you would have done to get to that goal in a serial execution. And so there's a simulation line where he kind of forces the execution of the serial code to look like the parallel code, and then gets a somewhat different looking speedup curve. But probably most well-known in this area is a language called Silk. And Silk is it was a language designed for shared memory machines, and the name stands for a language in the C ilk. So it's kind of like C. It's actually just a pretty small extension of C, as you'll see when I'll just show you a couple of examples of it. And there are a number of different applications that they wrote in Silk at the time. It was, so they started, so Charles Leiserson is at MIT. He created the Silk language there with students. Then they started a company called Silk Arts that commercialized it. Silk Arts was acquired by Intel. I think Intel has kind of stopped working on it, is my understanding right now, but I think there's now another effort by Charles to revive these ideas. But that's where I think for a while, you know, Intel, right after the multi-core things happened in 2005, there was a lot of interest in this, and that was when I think the acquisition happened. So what does Silk look like? This is not going to be a whole lecture on how to program in Silk, but just to give you an idea, it's a very simple extension, as I said. So here's the Silk code. With a function that you want to run in parallel, you put the word Silk in front of it, and inside of that function, then you can put the word spawn, so it's like a fork or whatever, which you have used, I guess, similar things. I guess OpenMP, depending on what kinds of pragmas you looked a little bit different. So there's spawn, say a sub function call, and then sync, which says wait for all of the spawned function calls that have been executed prior to getting to this sync point. So this is a really dumb way to compute Fibonacci, but nevertheless, it's a nice example that fits on a slide. It's got the two recursive calls that they're both going to be done in parallel. And one of the things that's nice about Silk is if you take out the Silk keywords, it is still a correct C program that will run. That's at least the way I've written it for this one. And in general, a Silk program is a correct C program. Whether it computes exactly what you want is a different question. So how does this execute? Well, let's say that we want to call Fibonacci of 4. Then that's going to create two subtasks, one of which is Fibonacci of 3, and the other one is Fibonacci of 2, which is going to turn into this kind of a computational DAG that gets unfolded like this. And they return, those are the upward arrows as those returning from the various function calls. And so there's a return happening all the way up to the top. So the blue nodes are the kind of the result of the return call. So what do they use in here? So they're going to use this idea of work stealing, and but they also use what's a greedy execution. So it's going to use that idea of stealing, kind of mostly executing from the top of the stack. So you're doing a depth first evaluation of this tree as long as you're executing locally. And when things get stolen, then when there's a node sitting in somebody's queue that is ready to execute, it can be stolen, and then that processor will execute down the tree using a depth first evaluation of the task graph. And so you can then call a thread is going to be ready to execute, or one of these tasks is ready if all of its predecessors have been executed. We of course don't know what the graph looks like ahead of this, what this gray stuff may look like, but at any given point in time, we have all the things that are ready to execute. And whenever there's a point in the execution, you've got some number of threads that are ready to execute. You'll run any P of them. So the runtime system has flexibility in terms of which ones to execute, and that will actually allow it to continue executing down a branch until it gets to a point where there's, say, multiple, like this yellow one has to stop here because this next node is not ready. So when the execution gets here, it will have to go and, say, steal some work from another place. And there's an incomplete step when there aren't that many threads left to execute. In which case you just run all of them. So there is a work stealer, and this has the idea of the stealing that I talked about before in terms of stealing from the what does it say? That from the bottom of the queue, which was the top of our stack before. So anyway, it's executing from one end and stealing from the other. And there's a nice theoretical result that says that the work stealing scheduler achieves expected running time of that TP, the parallel running time on P processors, is less than the running time on one processor, so the serial execution time divided by P, so that's perfect speed up, so it can't be any faster than perfect linear speed up, at least in this model. It's not taking into account cache effects or anything, plus some factor which is based on the worst, what happens if you were to run the problem on an infinite number of processors. So T infinity is running the problem on an infinite number of processors, and T1 is running on one processor, and so you can't go any faster than either of those two pieces. You can't go faster than linear speed up, and you can't go faster than what you would get if you ran it on an unbounded number of processors. So this is not really a proof of this idea, but kind of to give you a sketch, it says that a processor is either working or stealing at any given point in time. And so the total time that processors spend working is T1, right? That's the serial execution time. That's the total amount of work involved in the computation. And by the way, this sort of doesn't account for the fact that in certain tree search algorithms, you may find an answer and then cut off the rest of the tree search. This assumes you're going to do the same amount of work independent of the execution order. So that's where you would get those superlinear speedups in practice. So their model doesn't allow you to do superlinear speedups. It says you're going to always execute the same amount of work. So each steal has one chance over P of reducing the span by one. That is the span being the critical path length, because you find something that you can do. And so the expected number of steals is P times T infinity. And so since there's P processors, we get the expected running time that looks like this. So this is just kind of gives you sort of a sketch of how you get the fact that there are these two pieces of both the proof and the bound. There's also a space bound that comes from this, and I actually am not going to talk through this slide. It's got a bunch of text on it, except to say this depends on something called the busy leaves property, having to do with at what point you will execute any one of these, that you will always keep the leaves of the, if they're ready to execute, that you will always be executing those as long as you have enough processors to do it. But the space bound is actually quite weak, so it says that the space that's required to run on P processors is P times the amount of space that it took to run on one processor. So just, I mean, it is, by the way, better than no bound at all, but it is a pretty weak theoretical bound that says that, it's basically the amount of space you use on P processors is like you just made a copy of the problem on every one of those P processors. And so that's the best we can do so far. So there are other techniques for load balancing that are not based on randomization. A class of algorithms are called diffusion-based load balancing algorithms, where the machine is treated is going to be treated as some kind of a graph with some topology, whereas before I was assuming that it was equal cost to steal from any processor in the system. So now I could say, well, maybe it's not equal cost. Maybe some of the processors are nearby, which is actually the truth, although the difference between those costs may not be that large in an actual HPC system. But if I want to keep tasks that are nearby, only steal from things nearby, what I can do is build some kind of a logical kind of network or mesh of the processors and steal from the processors that are nearby you on that mesh. So this is analogous to the diffusion process, which we've talked about before, or certainly in Jim's lectures on sources of parallelism, but this is just saying that the work sort of diffuses between the system. So load balancing is definitely going to be slower than if you're using a randomized approach, but your locality is going to be better, and so if you have reasons to keep tasks nearby each other, you'll probably you can get better locality out of this kind of a diffusion-based approach. So there are some theory papers on this as well. Now there's other work that's been done on DAG scheduling, and this is a paper that's looking at a particular class of problems, which are direct solvers in linear algebra. So when Jim talked about linear algebra, right, you get a set of tasks that unfold, and they have dependencies between them, and so you can just sort of think of that. The way a lot of the parallel code is written is in these distinct phases, which is work on a column, work on a row, or a block column and a block row, and then work on the trailing submatrix. But this says, no, let me just think of the whole thing as a set of tasks, where a block row might have a set of a bunch of tasks within it, which are little B by B blocks of the matrix that you're going to do. and this gives you the unfolded looking task graph. So this is a what is this? This is a task graph for a pretty small, I think like a 3x3 sort of blocked Cholesky factorization. And I see a typo I have here, but the current scheduler from the University of Tennessee, so this is from Jack Dungaris, the group is called DAGUE, D-A-G-U-E, and it is it's a general library for, which was originally inspired, I think, by the work that they did on dense linear algebra and scheduling these kinds of task graphs. There's a bunch of other things in an OpenMP4, and that's going into GCC. There's also some work on these, and I think you even saw this in the when you're using OpenMP with the loops, you can give it various sort of scheduling annotations, but this would be for more of a DAG scheduler rather than just an iteration loop scheduler. You have a bunch of independent iterations of the loop. So where you have more interesting sort of graphs, there's a bunch of different things that have been developed over the years for different scenarios, both shared memory and distributed memory. So. But just to give you an idea of how many tasks there are in these things, so let's say that you've got you're looking for we're not talking about the DAG, which is the DAG of tasks, the graph of tasks, which are directed acyclic graphs, so that's the DAG. And so we've got an n by n matrix with b by b blocks. Well, each one of the tasks is going to be working on an n over b by n over b subproblem, which will turn into an n over b by n over b cubed task problem, and so there's going to be order a million. N over b is the number of tasks in each dimension for your b by b size tasks, and so you end up with a million of those for n equals 10,000 and b equals 100. So you end up with a lot of tasks is the basic point. So there are, as I said, a bunch of different schedulers that use different approaches. So Plasma, so these were all actually done by Jack and his group. The first one was doing static scheduling of the entire DAG, so just looking ahead. This is dense linear algebra, so for the most part you know in advance exactly what the DAG structure is as soon as you know n and you know b, and so you can actually statically schedule it in advance. The one thing that comes up is pivoting, so if you're swapping arrays, that can be a little bit unpredictable in terms of how the workload is going to unfold. Let's see, then Quark was doing more dynamic scheduling of the frontier of the DAG as you're executing it, because this became unwieldy in terms of the total cost of building and analyzing that task graph. So that was what the million example kind of shows you. And then the most recent version in DAG is the symbolic interpretation of the DAG, so they don't actually build the whole thing at once. And here's just a couple of performance numbers. So these are shared memory numbers. This is running on a 12-core system, and there's Plasma is the red line, Quark is the green line. So the two are pretty close in terms of the performance, the static one and the dynamic one. And MKL is the hand-optimized library from Intel. And let me not do all of these and just mention, we have also used these ideas on distributed memory. So this is looking at scheduling a task graph on a distributed memory setting where locality is so important. You don't really use any of these kind of stealing type of ideas. You actually do kind of predetermine where the tasks are going to run based on the data layout, so using kind of an owner computes rule, and this was actually written in UPC using a event-driven execution style by Perry Husband, so about 10 years ago, 11 years ago. So let's see, all of this is, work is very sensitive to the task size. So what I talked about early at the very beginning, you need to be very careful that you don't have tile sizes that are too small, and otherwise the cost of doing the dynamic load balancing, really the overhead of doing that will kill you. And and there's sort of an overall master task or process that is handling the task insertion, and that can also be a problem for scalability. So those, other than the UPC one that I just mentioned, most of this work was being done on shared memory, but they certainly have distributed memory work as well in Jack's group. So let me just skip and talk about another distributed memory case. So another one where load balancing becomes even more interesting is when the matrices are sparse. So now you still have this kind of non-trivial set of tasks that have to be executed, but some of them in the dense matrix are empty, so you don't have tasks there. And now you have an interesting task graph to schedule. And this was some work by Matthias Jacqueline along with Yili Zheng and Esma Ning and myself looking at writing this. And this was being written actually in an earlier version of UPC++. And there's the speed up numbers for that. So this was doing more of a, looking at the whole scheduling problem kind of in advance and then executing it. And so this was running on up to whatever 384 processors. I think that was on Edison. Yeah, on Edison. And that's why you get the weird number of processors, because there are 24 cores per node. And this is considered in the community, these kind of sparse factorization problems are some of the hardest things to parallelize. And having at least supervised students have worked on them for, I don't know, close to 20 years, I would say, these are problems in which you often have a lot more ideas of what you could do to try to make the code go faster, and each one of them is really difficult to implement because you just have this complicated task of things that you're executing and you don't have good estimates of the running time, and there's not as much computational intensity. So for example, in Silk, they find you can use work stealing and shared memory in order to do dense matrix multiply because the cost of those tasks is so high relative to the amount of data you're moving around. But with these sparse matrix problems, even though they're little matrix sub-problems, they're often sparse enough that their computational intensity isn't very high, and so the cost of load balancing can overwhelm the benefits of load balancing. Okay, last class of things, which I'll just give you a little bit more information about this, which is what happens if we've got tasks with communication. Well, so our communication pattern between a task could be some kind of a regular pattern. So the most common would be something like nearest neighbor. You've seen this in lots of different examples so far. You've got some kind of a mesh and you're doing nearest neighbor communication on that mesh. So the point is you've got a bunch of independent tasks, or a bunch of tasks I should say, but they're not entirely independent. They do have to communicate from time to time. And so how you now assign those tasks to processors can depend both on getting good load balance, but also getting good communication. And you'll see that this will come back in the cases where we can do it. We'll want to use graph partition if we can look at the graph in advance and then divide up the graph over the processors to minimize the number of communication edges that cross between the processor boundaries. And we can have, again, the semi-static case where we don't really know, where we can pre-compute what the communication pattern will be, but it's not necessarily something as fixed as it was in the static case. And then we've got the dynamic case where everything is completely unknown in terms of what's going to communicate with what. And so there again, in terms of hard problems to parallelize, a lot of things you've looked at direct and body. You looked at something that looked kind of like that with some cutoff homework 2. You've looked at problems that are the histogramming and hash tables are down here because the workload there is really depends on what the data looks like and what your hash function looks like, how you're distributing the elements, say the k-mers across the number of processors and things like that. So that one gets into the hardest class of problems. And this medium class, though, comes up a lot in scientific simulations where you can analyze the structure of the sparse matrix or of the mesh or whatever and come up with a predetermined schedule. So I'm not going to go through the slide again because I talked about graph partitioning, but when you have the information in advance of what you need to do, especially even if it's at runtime, then oftentimes if your computational intensity is pretty low, you want to run a graph partitioner to make sure that you aren't moving things around dynamically when you don't have to. And there are lots of kind of rules of thumb that come up in terms of how often you reload balance, things like that. You can let things get a little bit unbalanced for a while and reload balance every once in a while because running the graph partitioner is expensive. So there's all kinds of heuristics that come up here. I did want to mention a system called Charm++, built by Sanjay Kale at the University of Illinois, UIUC, and he's been building this system over many years and is really looking at these kind of iterative applications that are going to do something over and over again, whether it's moving a set of particles and calculating forces between particles, and that is the most widely used application written in Charm++ is NAMD, which is a molecular dynamics simulation. It is, by the way, a very computationally intensive problem because what you've got is a set of particles and you're computing forces between them. If you've got a subset of the particles, the cost of computing the interactions between those particles is very high, and so you can afford to move things around a little bit more aggressively in a problem like that. But he has then moved on to other sorts of problems, including adaptive meshes. I don't remember if he's done a sort of a Poisson kind of problem where the computational intensity gets to be lower. But that's something to always keep in mind is what's the cost of moving tasks and what is the cost of executing the task, and can you keep them, is it worth load balancing given those two numbers. And so in Charm what they do is you can also think of it as kind of like MPI, but you're going to over decompose your system. And so rather than just saying I have P processors, I'll divide the world into P tasks, I'll divide them into something called chars, which might be like 10 times more little chars than you have processors, and then the runtime system will move those around and manage them for you. So it helps with load imbalance. It automatically does some of the load imbalance for you. It also can help with failures because it can kind of recover it can keep track of what chars are around, and then sort of like MapReduce or something does in a cloud environment, it can go and retrieve those and try to rerun them, things like that, keeping lots of things into account. So you know what, I'm just going to give you a couple of, one picture of, there's really sort of a hierarchical scheme for load balancing, and this is again to get around the fact that things, it's kind of, you might have some locality that you're trying to preserve, so they use a hierarchical approach to load balancing where you mostly load balance within the neighbors of a tree, and then if you can't load balance that way, then it gets load balanced at the higher level, and you'll move things around between even the roots of the tree if you need to. Let's see, I didn't realize how many animations here. So they also have looked at keeping topology in mind when you're doing this kind of load balancing, and found that it was actually very important. So there was the topology oblivious algorithm. This is time per step, and you can see that it doesn't get any better as you add more cores. And this is also an impressive number of cores. They're running at 16,000 cores, and this is the NAMD code, and it's running on a Blue Gene P system, probably at Argonne. But if you take the topology of the network, which is a torus network, into account, and you use the hierarchical load balancing scheme that I talked about, things will tend to stay in a subtorus, and that gives you much better scaling than if you're there again doing something like random load balancing or whatever, or even aggressively load balancing across the entire system. So Sanjay's group at Illinois is not the only group that has used this. I mean, he works with others on the NAMD code and other applications, but I included this graph from Mike Norman, who's at UCSD, with a astrophysics simulation called ENSO, and this is a weak scaling example, so you're looking at efficiency here, and running up to the number of cores, which is about over 100,000 cores here, 200,000 cores. So very good scalability. Again, a weak scaling problem, but it's necessary. You really have to do weak scaling where you're going to go from 1 up to a couple 100,000. So nice results that you can get from that as well. So with that, I'll just wrap up and say, I mentioned this even just recently, but fundamentally there was always going to be there was a trade-off between load balancing and locality. And maybe the most obvious way of seeing that is if the only thing you care about locality, run everything on one processor, because then you've got no communication, and so there's no kind of locality costs in terms of communication between the tasks. Whereas, but you get terrible load balance, right? And so the other extreme is you spread everything out as much as possible, and you move everything around as much as you need in order to get good load balance, but that tends to cost you a lot in terms of locality. There's lots and lots of papers out there. It can be a little hard to kind of find your way through the different pieces of related work. Hopefully I gave you some pointers here to the different kinds of algorithms, so you can look, if you've got a problem that you think needs dynamic load balancing, you can at least look for some of those related papers. Since some of the ones I cited here are some of the older papers, you can look at who cites them and see if there are improvements in some of that work. I did a little bit of that myself this morning, but there's just an enormous literature of papers on load balancing, and some of it very significant, and some of it lots of minor tweaks on various things. So, you know, figuring out what to use means you have to understand your application domain. You need to understand what is known, at what point is it known, and how bad is your load balancing problem. And you may need to know something about, well, the machine. Well, certainly whether you've got a shared memory or distributed memory environment, whether you've got dependencies, you know, what is the variability in task costs, and how much communication do you have between tasks. And you know, sort of locality oblivious algorithms are versus locality kind of encouraged algorithms versus locality optimized algorithms. I mean, there's all different sort of ways of putting emphasis on locality or not putting emphasis on locality. And as I said before, exactly when you know the information and therefore how you're going to use it is really important to coming up with a load balancing strategy. And right, so one of the questions that came up early on in the discussions about exascale computing was looking back at some of that slide I showed really almost at the beginning, looking at load imbalance from ECC, memory error correction, or load imbalance from operating system effects, was the idea that the processors were going to be heterogeneous and require dynamic load balancing even if the application code did not. And that we still have issues. I mean, what has become more of a problem, and one of the reasons there was a lot of concern about it, was dynamic clock speed scaling. And so the fact that the processors run at different speeds depending on either their heat or their power draw, exactly what computation they're doing at a given point in time can change their performance. And so there is an increased interest in it as we look towards future architectures that may have some variable performance effects. Any questions? Okay. Well, thanks very much, and this is, I think, my last lecture, so I will look forward to seeing you all at the poster session. There were a couple of you that I sent, and may or may not be in the room, but I did send mail to a couple people about talking about projects, so feel free to contact me if you want to talk about anything related to either genomics or UPC++ or anything like that. Okay, thanks very much.